All right, so let's start the problem solving lecture for chapter 8. So this is the first question. So let's see what it asks us to calculate. Okay, so we have a carousel and it is initially at rest. Okay, so at t equal to 0, it is at rest. So that means we can write W, I mean, not W, I'm sorry, the omega. Okay, so omega 0 is equal to 0. So that's the first thing we are given. Okay, and it said that at equal to at t equal to 0, it's given a constant angular acceleration. Okay, it was at rest, but then we have an acceleration, I mean an angular acceleration that is equal to 0.060 rad per second square, which increases its angular velocity for 8 seconds. And it makes sense. So when there is an acceleration, the velocity will increase. Okay, so the angular velocity will increase, and it increases for t equal to 8 seconds. So if so, what is the angular velocity of the carousel at t equal to 8 seconds? So the first question is this one. So we know that W, I mean, again, I'm sorry, it's omega equal to omega 0 plus alpha t. So this is one of the equation. One of the equation means one of the kinematic equation we already learned in class. So this is the equation which we can use to solve this problem. Okay, so omega equal to, so this is 0, so we don't need it, so it's equal to alpha t. Alpha is given 0.060 rad per second square. T is given, that is 8 seconds. So the omega at 8 seconds is equal to 0.48 omega is rad per second. Okay, so A, the angular velocity of the carousel at 8 seconds is 0.48 rad per second. Okay, now we have to calculate the linear velocity of the child who is at 2.5 meter from the center. Center means the axis of rotation. Okay, now this can be determined by using this equation. R is 2.5 meter and omega is 0.48 rad per second. Okay, so this gives us 1.2. So 1.2, and because this is linear velocity, it should be meter per second. All right, so let me use another color. Now number C, the tangential acceleration of the child and the centripetal acceleration of the child and the total acceleration. Okay, so the tangential acceleration A10 was, if you remember, it was R alpha, right? So R is 2.5 meter and alpha is equal to this, and this gives us 0.15 meter per second square. D, centripetal acceleration, is, so you can either use this or you can use R omega square. So both should give you the same value. So let me use this one. So this is equal to this is equal to 0.58 meter per second square. And lastly, the total linear acceleration. So this is linear acceleration, this is also linear acceleration, and you know that the tangential acceleration and the centripetal acceleration are always perpendicular to each other. So the total linear acceleration can be determined by using the Pythagorean theorem. Okay, so 10 is 0.15 meter per second square plus 0.58 meter per second square, and that is equal to 0.60 meter per second square. So the total linear acceleration for the carousel for the child is 0.60 meter per second square. Okay, all right. Number 2. So what we have here, so we have a centrifuge rotor that is accelerated from rest. So again here omega 0, so this is rest, that means omega 0 equal to 0 to this RPM in 30 seconds. So t equal to 30 seconds, but here this is frequency in RPM. Okay, so from frequency you can determine the angular velocity. Okay, so and then we have to calculate what is the average angular acceleration. Okay, all right, so first let's calculate this and then move on to the second one. So first we need to calculate omega. So omega equal to 2 pi f. So one of the mathematical definition we derived was this. So 2 pi and f is 20,000 RPM. Okay, now you know that RPM means revolution per minute, and it's not standard international unit, so we have to convert it into rep per second. So we can do it by dividing it by 60. Okay, and then it is rep per second. Okay, so this number in now rep per second. So when you multiply it by 2 pi, it gives us something like this. So I get 2094.4. So when you multiply by 2 pi, it becomes rad per second. Okay, because omega, so omega's unit is radian per second. Okay, so this is omega. Now what is alpha then? Alpha can be determined by using either from delta omega delta t, or you can also use omega equal to omega 0 plus alpha t. Okay, so both will be will give you the same thing. So let's use this. Okay, this equation. So we know that omega is omega, we already know. Omega 0 is 0, then alpha t. So if I solve this equation for alpha, okay, it gives me alpha equal to omega over t. Okay, so that means alpha is 2094.4 rad per second divided by 30 seconds, and this is this is 69.8 rad per second square. Okay, so the acceleration, the angular acceleration we get here for number A is 69.8 rad per second square. All right, now number B. Okay, so number B, it asks us to how many revolutions has the centrifuge rotor turned during its acceleration. So revolution is basically related, I mean, number of rev is related to angular displacement. Okay, so if you can calculate angular displacement, you can immediately tell how many revolutions. Okay, so what is the angular displacement? So if you remember from the theory class, I mean from the theory lecture, angular displacement is basically theta. And theta can be determined from this equation. Okay, so one of the kinematic equation we derived is this one. Okay, now here we know everything on the right hand side. So if you plug all the value, all the known values on the right hand side, we can determine theta, and then we can convert it into the number of revolutions. Okay, so what is this? So this is 0, right? Because omega 0 is 0, so this is 0, so it's even simple. Okay, so we have half, and then alpha is equal to 69.8 rad per second square, and then t is 30 second, that is square. So total theta I got is 31,410, and it is radian. Okay, but the question asks us to calculate number of revolutions. Okay, so we have to convert this number to number, this radian to number. So now you know that for each turn, okay, so for each turn, I mean each revolution, okay, it travels 2 pi radian, right? So this is half pi, this is pi, another half pi, this is another half pi. So total radian it travels is 2 pi. So 2 pi radian is equal to 1 rev, revolution. Okay, so how many revolution is done in this rad? Okay, so you can determine the number of turns or number of revolutions by dividing this number by 2 pi. Okay, so if you divide this by 2 pi, it gives us 5,000. So 5,000 rev. So here the number of revolutions for this problem is 5,000. Okay, all right. All right, so this is the problem about rolling. Okay, so let's see what it asks us to calculate. All right, so a bicycle slows down uniformly from, so here you see that it's the linear velocity. So linear initial velocity is given, and it stops somewhere here. Okay, so the initial velocity is this, final linear velocity is equal to 0. Okay, and the distance from here to here, it's also given, it's 115. Okay, so if so, then what is the angular velocity of the wheel at the initial instant? So first you have to calculate the angular velocity at this point. So we have to basically calculate omega 0. So omega 0 is what? If the diameter of the wheel is 68 centimeter. So diameter means this distance, I mean this length. Okay, now you know that diameter is given 68 centimeter, or in meter it will be 68 times 10 to the power minus 2 meter. So it's basically 0.68 meter. And the radius is half of diameter. So it will be 0.68 divided by 2. And this is 0.34 meter. So the radius of this wheel is 0.34 meter, and the angular velocity, you know that, okay, so the linear velocity is related to the angular velocity by this equation. So omega 0 will be V0 divided by R. So as V0 is 8.40 meter per second and radius is 0.34 meter. Okay, so the initial angular velocity will be 24.7 rad per second. Okay, so that is basically the first one. The second one is the total number of revolutions each wheel rotates before coming to rest. Okay, again, the number of revolutions means we have to calculate first theta, and then we have to divide it by 2 pi to get the number of revolutions. Okay, so theta can be determined in many ways here. Okay, but the easiest way is to do is this one. Number B, easiest way to calculate theta is to use this equation, L equal to R theta. So theta equal to L over R. So L is this linear length. Okay, 115 meter. Okay, so for this 115 meter of linear length, what is the corresponding theta? And we already know R equal to 0.34 meter. Okay, so this gives us theta equal to 338.2 radian. Okay, so this is in radian. So similar to the last problem, if I want to know number of revolution, okay, we have to divide it by 2 pi. Okay, so if you divide it by 2 pi, it gives you 53.8 rev. Okay, so this is the number of revolutions. Okay, all right, the third problem, it asks us to calculate the angular acceleration of the wheel. Okay, so the angular acceleration of the wheel and then the time. Okay, so angular acceleration and time. Okay, so again, there are many ways to do that, to calculate the angular acceleration. Okay, so let me erase this part. Okay, all right, so here number C, I am interested on alpha. Okay, so alpha can be determined from this equation, omega square equal to omega 0 square plus 2 alpha theta. Okay, and as you know that omega equal to 0, the final velocity is equal to 0, so that means final angular velocity is also equal to 0. Okay, the bike slows down to rest. Okay, so slows down to rest, both angular and linear velocity is equal to 0, so the final velocity is equal to 0. So this means this is equal to 0. So the equation is now simpler. Okay, so we have to calculate alpha. So 2 alpha theta equal to minus omega 0 square. So alpha equal to minus omega 0 square divided by 2 theta. Okay, now omega 0 we calculated in the first problem and it was 24.7 radian per second. So that is the omega 0. All right. And then theta is, so make sure you don't use this number for theta. Okay, so this is not theta, this is the number of revolution. The theta is this number. Okay, so make sure you understand this. Theta should be in radian, not in rev. Okay, so what you have to substitute is this value 338.2 rad. Okay, so if you substitute this value, it will be different, you'll get a incorrect answer. Okay, so once you plug all these values, you should get what I got in my calculator is these values, negative 0.902 rad per second square. Okay, so you can use this equation to solve this, or you can even use this equation. So v square equal to v0 square plus 2a x minus x0. Okay, so this equation will give you a. Okay, so you can solve this equation for a, and then define and determine alpha from a. Okay, how? From alpha, I mean, you can use a over r, because a equal to r alpha. Okay, so you can use this or you can use this, so whatever you prefer should be fine. Okay, all right, the last thing here we have to calculate is the time to go from here to here. Okay, all right. So time can be determined by using this equation, omega equal to omega 0 plus alpha t. So this is 0. So if I solve it for t, it gives me this. So t equal to minus omega 0 over alpha, and omega 0, the first problem gives us this. And then we calculated alpha equal to 0.902 rad per second square. So this minus cancel out, and we get t equal to 27.4 second. Okay, so the time we get here is 27.4 second. All right. All right, so now let's solve a problem about torque. Okay, so remember that torque is defined as something like this: tau equal to r f sine theta, where r is the lever arm and lever arm is the distance or the length from the center from the axis of rotation to the point where the force is applied, and f is the force, and sine theta is the angle between r and f. Okay, so first let's calculate for this one, for fa. Okay, and let me call it this tau a. Okay, now this is the center. Okay, now from here to here is the distance is ra, so it will be ra. So this is the lever arm, and then fa, and the angle between ra and fa is sine 90 degree, right? So it is sine 90 degree. Now here you have to also understand whether it is moving, I mean rotating clockwise or counterclockwise. Okay, so you have to put the sign explicitly here in this equation. For example, if I apply a force here in this direction, so this is the direction of FA, the disc will rotate in this direction, right? And this is counterclockwise. Okay, counterclockwise means positive sign. So the sign here will be positive. Okay, so positive sign, RA is 30 centimeter. So 30 times 10 to the power minus 2 meter. FA is 50 Newton and sine 90 degrees 1. So this gives us 15 Newton, 15 and positive 15 meter Newton. So the torque for this one is plus 15 meter Newton. Okay. So similarly, let's do the same thing for this force. Okay. So tau B RB. So RB is the distance from here to here. So this is the lever arm. Okay. And it's already given in the question. And FB. Okay. Now, what is the angle? Angle between RB and FB is this angle, okay, or this angle, okay. So you can either use this angle or this angle, okay. Now this here you have to be careful, okay. Many students make mistake here. So this angle is 90 degrees. So 90 plus 30 is 120 degree. So either you have to use 120 degree, or you see that this is already given 60 degree. Okay, so you have to understand how the angle is determined here. So it will be either sine 120 degree or 60 degree. Both give the same numerical value. So let me use 120 degree. So once you have that, then you have to explicitly use the sign. Okay, so when we have a force, here, okay, so the disc will rotate in this direction, and this is the clockwise direction, and clockwise, you know that the sign is negative, so we have to use a negative sign here, and this is very important to understand. So negative, and then 50 times 10 to the power minus 2 meter, it's also 50 Newton, and then sine 120 degree. So if you plug all this value in your calculator correctly, it should give you negative 21.7 meter Newton. Okay. So the net force, net torque is plus 15 meter Newton minus 21.7 meter Newton, and that is equal to negative 6.7 meter Newton. And this negative sign tells us that net rotation will be clockwise. Okay. All right. All right, so this is the problem about the moment of inertia. Okay, so remember that moment of inertia for the single particle, it was mr square. Okay, if we have more than one particle, if we have more than one object, for example, here we have two objects, so it will be m1r1 square, m2r2 square. So here m1 is the mass of one object, m2 is another object, and r1 is the distance from the axis of rotation to the object 1, and r2 is the distance of the object 2 from the axis of rotation. Okay, so this is the equation. So then we have to determine I for two different orientation, two different axes of rotation. For the first one, so this one is the axis of rotation, and for the second one, this is the axis of rotation. Okay, so let's try to determine this. So for first one, I equal to, so object, let me call it M1, and this is M2, M1 and M2. So this is 7 kilogram. So R1 for M1, it is this distance, right? And because it is the center, okay, it will be 2 meter. So 2 meters square. And M2 is what? M2 is 5 kilogram. And R2 is negative 2 meter, but it is square. Okay, so negative because it is on the negative side. Okay, so if we think that this is the origin, this is the negative side. Okay, so that's why I wrote negative 2 for 5 kilogram. But even if you use the positive sign, you will get the correct answer, because negative of some square is positive. So no matter whether you use a positive sign or negative sign here, it will be give you the same result. But I mean, we should use the correct correct sign. Okay, all right. So then plugging all this value in your calculator should give you 48 kilogram meter square. All right, and number B is the same thing, similar thing. So this is M1. So from here, from the axis of rotation to M1 is 4 meter, plus you see that between this and this is 0.50 meter. So it will be 4.50 meter square for M1. For M2, it will be just 0.50 meter. So then it will give you 143 kg meter square. Okay, so you see that when you change the axis of rotation for the same system, the moment of inertia changes. Okay, all right. All right, so here in this problem, we are going to use the torque as well as the Newton's, the rotational equivalent of Newton's second law. Okay, all right. So we have this object. Okay, this looks like a disc, and it rotates about this point. Okay, the center. So this is the center axis of rotation, and it says that a force Ft is applied here. Okay, so the value of Ft is 15 Newton, and R0 is given. The radius of this disc is given. Okay, and mass of this disc is also given, 4 kilogram. And then what else given? The pulley accelerates uniformly from rest to an angular speed of 30 rad per second in 3 seconds. Okay, now it also said that the frictional torque, if the frictional torque is this, what is the moment of inertia of the pulley? Okay, now it's not regular disc. So if it is regular disc, something like this, okay, solid uniform disc, we can use the moment of inertia from the least we discussed during the class, but it's not regular disc. Okay, so we have to use something else. Okay, so let's use something else first. Okay, so you know that we can determine tau, right? Tau from this equation, RF, actually FT, okay, and R0 sine theta, from this equation, right? R0 is this, FT is this. Okay, then we can also determine tau equal to I alpha. Okay, so tau is this value from this equation, and then alpha we can determine from this information. Okay, so then from these two definition of tau we can determine I. Okay, so first let's determine tau for this ft. Okay, so what is the tau for this ft? Tau, let me call it tau t. Tau t will be R0, the lever arm, the force, and you see the angle is sine 90 degree. So sine 90 degree. So this angle is 90 degree. Okay, and what is the sign here? So when you apply a force here, it will rotate in this direction. Okay, so because it will rotate in this direction, it is counterclockwise. Counterclockwise means positive sign. Okay, so positive sign R0 is 330 times 10 to the power minus 2 meter. Okay, it's in centimeters, so we have to convert it into meter, and then ft is given 15 Newton. Okay, and sine 90 degrees 1, so this gives us plus 4.95 meter Newton. Okay, all right, so this is the torque by this force. Okay, now there is also a frictional torque. Okay, and you know that friction is always opposes the motion. Okay, so in linear or translational motion you see that friction opposes the motion. So here friction opposes the rotation. Okay, so what it means if the applied torque is positive, so here you see that it is positive. Okay, so although it did not say whether it would be negative, I mean the torque, friction torque will be negative or not. So by looking this, okay, and by knowing that friction always opposes the motion, so here friction opposes the rotation. Okay, friction opposes the rotation here. Okay, so if the applied torque is positive, friction torque will be negative, so it would be this. Okay, so then net torque will be plus 4.95 minus 1.10 meter Newton, and that is plus 3.85 885 meter Newton. Okay, so this is the net torque, or the net torque, or not. We normally use this symbol, not net. So let's use this. Now let's try to determine alpha. Okay, so what is alpha? So alpha is this. Alpha equal to delta omega delta t. Okay, so omega is final minus initial delta t. Okay, so here final is 30 rad per second, initial is 0 because the object, I mean it starts from rest. Okay, so it says that from rest to an angular speed of 30. So 30 is final, 0 is initial, and the time is 3 seconds. Okay, so the alpha here is 10 rad per second square. Okay, now come back to this equation. So here tau equal to I alpha. So this is the Newton's, I mean the rotational equivalent of Newton's second law. And on the right hand side we have 3.85 meter Newton, and the left hand side we have I alpha. So I is 3.85 meter Newton divided by alpha, and alpha is 10. So this 10. rad per second square. So what we get is this 0.385 kilogram meter square. So the moment of inertia for this disc is 0.385 kilogram meter square. All right, so we have few more problems. We'll be doing it in the next lecture.